Welcome back. We march on through our look at applications of integration. We begin today to look at volumes by what are called cylindrical shells. So if I may, we'll pretend for the moment that you have some function. This is the graph of the parabola, y equals 4 minus x squared. This is the region from 0 to 2. We're going to take this region and revolve it about the y-axis. So we imagine some solid that looks like so. It's got a circular base. We've spun around. It looks like that. That's the solid. The slices that I would like to take are dx slices. They are vertical slices. When you spin a vertical slice around the y-axis, you don't get a disc, you don't get a washer like we did in the previous lesson. You get what's essentially a paper towel roll. You get a very thin rectangle that's been spun around. You get essentially a paper towel roll. So the question is, what is the volume of a paper towel roll? Well, now we're not interested in what goes inside the paper towel roll. We're interested in how much cardboard makes up the paper towel roll. So if we were to cut with scissors down here and unroll the roll, we would end up with something that looks like this. A very thin rectangle of cardboard. So what's the volume of a very thin rectangle of cardboard? Length, width, depth. The depth, that's easy. This distance is the same as this distance. The depth is easy. The length and the width, not so much. So what's this distance? Where is this in this picture? Well, the height of the paper towel roll should be the same as this height here. So whatever the function is this height? Whatever the function is. And then there's this question. Where is this distance in this picture? Well, this distance is here. It's the circumference of a circle. So how do you find the circumference of a circle? It's 2 pi times the radius. So what happens? Well, we nest a bunch of these paper towel rolls inside each other, and we create this solid from a bunch of nested paper towel rolls. So to do that, we have to make the paper towel rolls thinner and thinner and thinner, which means the delta x gets smaller and smaller and smaller, which means there are more and more and more paper towel rolls. And so eventually, the volume we're looking for is the integral of 2 pi times the radius. But what's that radius? That radius is whatever this x value is. And then the height and delta x becomes dx. From where to where? From 0 to 2. This is the method of cylindrical shells. 2 pi times a radius takes care of the length of the paper towel roll. The function is the height, and then the delta x becomes a dx, and we integrate. So in general, the volume by cylindrical shells is an integral from a to b of 2 pi times a radius times a height dx. Okay, I will demonstrate. Suppose this would technically be example 2. You have some region. That region is the region under the parabola y equals 6x minus x squared. This is the region from 0 to 6. I'm going to take that region and revolve it about the y-axis. This is not a question that we could do by discs or washers easily. If we sliced this way, those slices would start and end on the green curve. So it's very difficult for us to talk about how to do this by discs or washers. We would need a different expression for this branch of the parabola as we had for that branch of the parabola. I would like to slice this way and spin that around, get ourselves a paper towel roll. So what is the volume? The volume is the integral from 0 to 6 of 2 pi times the radius times the height times the thickness. The radius of the paper towel roll goes from 0 to whatever this x value is. That's the radius. The height of the paper towel roll is whatever the function value is. That's 6x minus x squared. So we can pull the 2 pi out. We can distribute this x. And then it's all fundamental theorem part 2. Fundamental theorem part 2 says we find an antiderivative. We find an antiderivative. We substitute the 6. We substitute the 0 and subtract. It turns out that 2 times 6 cubed is 432, and 6 to the 4th divided by 4 is 324, and that gives us an answer of 216 pi. I will do another video that lays out some examples just to drive the point home, but this is the basic content behind volumes by cylindrical shells. I hope that it is helpful to you.